Good evening, everyone. On behalf of the Computer Society of India, Vellore chapter, I extend a very warm welcome to all our esteemed guests, faculty members, and participants. Thank you for joining us for today's webinar, The Secret Life of Distributed Systems, How Netflix, WhatsApp, and Bitcoin Scaled to Millions. Every day, we send messages on WhatsApp, stream our favorite shows on Netflix, and make seamless UPI payments. Although these platforms serve very different purposes, they are all built to solve a common challenge: designing systems that can reliably scale to millions of users. Today's session will explore why distributed systems are at the heart of modern applications, the challenges they address, and how popular platforms overcome them using concepts like caching, fault tolerance, consensus, and observability. Through this session, we'll build an intuitive understanding of how these systems work. The agenda of today's session is to explore why distributed systems matter, the challenges of building large-scale applications, and how platforms like WhatsApp, Netflix, Google Docs, etc. address them. To cover key concepts through real-world examples before wrapping up with a summary and an interactive Q&A session. Now, I would like to invite Professor Saravana Kumar R. to give a brief overview of the monthly CSI Region 7 student-led webinar series. Professor Saravana Kumar is a professor of practice at Sri Ramakrishna Engineering College and a visiting professor at PSG College of Technology. With over 30 years of industry experience, he has served as director at Cognizant Technology Solutions and consultant at Tata Consultancy Services. He also served as the chairman of the Computer Society of India Coimbatore chapter and was a CSI G20 ambassador for Tamil Nadu. Over to you, sir.
Thank you, Harshita. Iniya Malai Vanakkam. Good evening, everyone. It is my pleasure to welcome you all to the CSI Region 7 student-led webinar series, a unique national level initiative conducted on the last Saturday of every month. This webinar series provides students with an opportunity to present on emerging technologies before a national audience comprising of students, faculty members, researchers, and industry professionals. Every session is mentored by experts who guide the student speakers on technical content, presentation skills, and best practices. Our objective is to nurture confident, competent, and industry-ready student leaders while promoting a culture of knowledge, sharing, and peer learning. Today's webinar, The Secret Life of Distributed Systems, How Netflix, WhatsApp, and Bitcoin Scale to Millions, takes us into the fascinating world of distributed systems that power many of the digital services we use every single day. Have you ever wondered how Netflix streams seamlessly, WhatsApp delivers billions of messages, or Bitcoin operates without a central authority? Behind these platforms are distributed systems that enable them to handle millions of users simultaneously while delivering speed, reliability, and resilience. During this session, you will discover how modern applications overcome challenges such as communication, latency, failures, and coordination, and also learn the concepts that enable them to scale seamlessly. Through simple explanations and real-world examples, you will gain a better understanding of the technology behind today's most popular digital platforms. Whether you are a student, faculty member, researcher, or industry professional, I'm confident that this session will provide valuable insights into the fascinating world of distributed systems. With that, now I hand over the proceedings to Harshita, who will introduce our speaker for today's webinar. Thank you and wish you all an engaging and insightful session. Thank you.
Thank you, sir. As chief guest today, we have with us Dr. Inya Nehru. Dr. Nehru is currently a professor at VIT Chennai and brings with him nearly 4 decades of experience in academia and public sector technology. He has previously served as a Deputy Director General at the National Informatics Center, Ministry of Electronics and Information Technology, Government of India, where he led several e-governance initiatives and headed the Open Technology Center. Prior to that, he served as Senior Technical Director at NIC, overseeing network and infrastructure services for over 3 decades. We are truly honored to have you with us today, sir.
Thank you, Ma. Today, we are going to listen the topic from Mr. Ojaswi Om. Actually, many of you know the distributed systems has grown over the period of time, and today you hear about cloud computing, you hear about parallel processing. Everything is possible because of the tremendous growth in the field of distributed system. As all of you know, distributed system brings with itself a lot of advantages. Some of the advantages of distributed system, as you know, it is basically resource sharing, where we have multiple systems spread across the world, and it provides very high reliability, so that even if one system fails somewhere in the corner of the world, the other systems can easily take over. The distributed system also helps in fault tolerant system, which can definitely provides more reliability and scalability. The distributed systems, as you know, today the topic is how quick we can scale when we go for a distributed systems, where from a few thousand hits today, we talk in terms of few lakhs of hits happening in the internet world. And definitely, it gives an improved performance. And with this, it brings the concept of load balancing across the various systems spread across the world. And the main advantage of distributed systems has been the geographic accessibility, where people who are in different parts of the world can access the nearest system and still get the convenience of accessing all the resources, whatever they need. And in turn, it provides the very cost-effective solution. So distributed system provides a low cost. As many of you know, cloud provides a pay-per-use model where heavy investment of infrastructure is not needed, and you pay only for the time or the resources what you are going to use. But having said the advantage of distributed system, we also have some challenges associated with the distributed system. I think Ojaswi will be explaining in detail about the challenges. And one or two I'd like to mention is that we have a complex design, and when we go for a distributed system and the systems are spread across, the management also may turn out to be a little bit challenging. And there is a lot of dependency on network. So network, the percentage of the uptime of the network is equally important. And due to some reason, if the network is going to fail, we are going to face multiple problems. And as you know, even though the distributed system provides a lot of advantages in terms of reliability, there is associated risk, security risk involved. So we should understand when we have a distributed system, what kind of security mechanisms have to be put in place, and so that security which is not should not be compromised. Again, we have a data consistency. When we replicate in multiple servers, we may face the problem of data consistency if it is not updated synchronously. So that is also a big challenge. There could be a communication overhead also, where there could be a slight performance hit when we are going to use a distributed system. So, and it sometimes also have, whenever there is some debug notice, it could be slightly difficult to debug. So we are facing increased challenges in terms of software complexity and time synchronization also when we go for distributed system. I'm happy that my parent organization VIT Vellore student Mr. Ojaswi is going to talk the need of the day, what distributed system which is helping us to scale. High scalability is being achieved, but with that we have challenges. And I think this particular webinar will help the students to understand and not only the advantages of distributed system, but also the limitations and how to overcome the limitation. I expect other students who are hearing or viewing this webinar should also come forward and talk in the CSI webinar, which is organized by Mr. Subramaniam sir and Dr. Saravana Kumar sir, so that this will open a wide range for the youngster, for the Gen Z kids to not only address the technological problem, but the readiness of the younger generation to face such challenges. I thank the Region 7 for giving an opportunity. Thank you very much, sir.
Thank you so much, sir. It is now my pleasure to introduce our speaker for today, Ojaswi Om, Senior Co-Member at CSI VIT. Through this session, he will help us understand the principles behind some of the world's most scalable software systems and provide a practical perspective on distributed systems. Over to you, Ojaswi.
Could you please give a brief introduction about Ojaswi?
Ojaswi Om is a senior co-member at CSI Vellore chapter, actively participating in all tech discussions and project initiatives at CSI.
Yes. Good evening, everyone.
Possibly Ojaswi can introduce himself for a minute before he proceeds. Yeah, that will be better.
Yes, Ojaswi, please go ahead.
Yes, sir. So I am a senior member at CSI VIT, and I've been particularly invested in this subject of distributed systems. I take a lot of interest in how things scale in real life and how the systems that we use in everyday life, such as WhatsApp or Netflix or Google Docs, they seem very different, but they all seem to solve an underlying problem, which is the same. So I am always interested about learning how there's a commonality in all different things which may seem unrelated. Um, Thanks, sir, for a very great introduction to the subject. There are many things that he said which I'll be repeating, so I apologize for that. It was very verbose. And yeah, we start with distributed systems and the life of how they are similar. Whether you're publishing research on consensus protocols or engineering microservices to handle billions of requests per second, the fundamental challenges we face are identical. Today, we will be bridging the gaps between rigorous computer science theory and real-world industrial architecture. If you look at the platforms that we use daily, WhatsApp, Netflix, Google Docs, UPI, Bitcoin, and even Uber or Ola, on the surface, they seem completely unrelated. One of them streams movies, another processes financial transactions, and another tracks rides. But beneath the user interface, every single one of these actions conceals an enormous distributed system. When you tap send or pay, your request initiates an intricate data flow across hundreds of networked servers. Understanding their shared architectural DNA sheds light on how modern applications survive and operate at a global scale. It may seem very simple on the surface, but it is actually a huge iceberg type situation happening underneath. Whatever you see, it's a complex network of multiple systems across the world, which is coming together to give you the services you use. So what formally defines a distributed system?
Sorry,
It is
Ojaswi.
a collection.
Ojaswi, sorry, your voice is
Yes, sir.
not so clear actually. Any setting needs to be changed. Please do it so that your voice is clearer. Thank you.
Okay, give me just 1 second. Is this better?
I think the same. It's okay. If we do not have a choice, it's okay. Let us continue. No worries. Yeah, thank you.
Okay, so I apologize for the inconvenience. Okay, so what formally defines a distributed system? It is a collection of independent computers that coordinate so seamlessly they appear to the user as a single coherent machine. The question is, why do we go through all this complexity? Why not just buy one massive,
Sorry,
powerful
Ojaswi,
computer?
you are having hand mic, huh?
So I've got earbuds.
Earbud. Slightly you can be away from that. I think some slightly away. Just try. Yeah. Now we can talk. Proceed.
Yes, I think it's the fan interfering with the mic.
Yeah, it's okay now. Yeah.
Okay, sir. Okay, so why go through all this complexity? Why not just buy one massive, powerful computer? To this, there are two reasons: scaling and reliability. There are two concepts to scaling. One is vertical, where you add more RAM, more CPU to a single mainframe. But there are physical and economic limits to this. If you need to pull a heavier load, you cannot have a infinitely larger computer. If you talk about analogies, if you have to pull 10 people, you can maybe have a horse carriage. But if you need to pull 1,000 people, you cannot just get a bigger horse. That has to stop somewhere. Now there is the concept of horizontal scaling, which is adding multiple horses and multiple carriages to have better performance and to serve the needs that we have. Furthermore, a single machine is also a single point of failure. Let's say we have a supercomputer. If there's only one of them, if it dies, the entire business experiences a total outage. Distributing components across nodes minimizes the blast radius of isolated hardware failures. To understand where we are, we look at three pivotal milestones in our field. In 2000, Eric Brewer formalized the CAP theorem, establishing the theoretical boundaries of what distributed databases can achieve. CAP theorem stands for consistency, availability, and partition tolerance. It describes the trade-offs that distributed data stores must take when faced with network partitions. Then, in 2008, Bitcoin proved Byzantine fault-tolerant consensus could operate at a global trustless scale. And in 2012, Google Spanner challenged conventional wisdom by achieving globally distributed, strong external consistency using atomic clocks and GPS receivers. These milestones represent the continuous dialogue between academic theory and industry innovation. Now, the thing is, between all these computers, the biggest challenge is communication. A single server in isolation might boast what we call five nines or 99.999% uptime. But the moment you connect two servers over a network, you introduce chaos. We are bound by the physics of communication. The speed of light is finite. You cannot send data from Tokyo to London instantly. Latency is a physical constraint that we must architect around. Furthermore, Peter Deutsch outlined in the policies of distributed computing, we can never assume the network is reliable. Packets get delayed, duplicated, or sometimes dropped entirely. Our architectures must treat network failure not as an anomaly, but as the baseline reality. This leads us to the most difficult problem in distributed computing, partial failures. In a single machine, if the OS crashes, everything stops. In a distributed system, node A might crash while node B keeps running, and node C cannot tell if node A is dead or just slow. How do we make sense of events when partial failures occur? We look at time. But here's the catch: there's no universal global clock. Even with NTP synchronization, clock drift leaves us with discrepancies of 1 to 10 milliseconds. In situations such as high-frequency trading or distributed databases, 10 milliseconds is an eternity. Therefore, industry and academia rely on logical clocks to track the causality of events, determining what happened before without relying on physical time. Now we move on to CAP theorem. When network partitions inevitably happen, we run headfirst into this. You must make a fundamental trade-off. Do you prioritize consistency, which is ensuring every read returns the most recent write, even if it means rejecting requests during a partition? Or do you choose availability, guaranteeing success to every request, even if the data it might be temporarily outdated? You cannot have both during a network split. Understanding this trade-off is critical because at scale, failures are not exceptions, they are inevitable. The more components you add, the higher your cumulative probability of failure. Resilient systems are designed to degrade gracefully rather than fail catastrophically. Let's transition to the key architectural patterns that we use to solve these challenges, starting with caching and CDNs. To overcome network latency and read bottlenecks, we serve data from hierarchical storage layers closer to the compute engine. But as Phil Carlton famously said, there are only two things in computer science: cache invalidation and naming things. Ensuring cache coherence, preventing users from seeing stale data when the underlying source changes, requires robust invalidation strategies. When we push caching to the global state, we get CDN, which stands for Content Delivery Networks. By serving media and static assets from geographically distributed edge servers, we drastically reduce latency and lower origin server bandwidth costs. This means that wherever your network requires to be used, you have databases stored over there, geographically closer to the users, instead of having just one server remotely located. This also enables cost efficiency because having excuse me, because having one server with a lot of bandwidth is not feasible as compared to having multiple local servers to decrease bandwidth costs and ensure delivery speed. Now we come to replication and partitioning, also known as sharding. When datasets outgrow a single machine, we apply two fundamental techniques, replication and partitioning. Replication creates redundant copies of data across multiple nodes to guarantee availability and fault tolerance. Whether using leader-follower or leaderless architecture, the challenge lies in balancing strong versus eventual consistency across replicas. Simultaneously, we use partitioning or sharding to divide large datasets across different machines. To manage dynamic sharding without causing system-wide data migrations, we employ consistent hashing. This mathematical strategy ensures that when a node is added or removed, only a minimal fraction of keys need to be remapped, preventing data hotspots and traffic congestion. And to distribute incoming traffic across our replicated computer nodes, we rely on load balancing. Think of a load balancer as a store manager, excuse me, directing shoppers to the shortest supermarket checkout lanes. If there's only two lanes and all the people that are in the store at one time are on one lane, the second lane is not utilized to its max potential. So what we do is we keep a store manager who can divide people evenly across both the lanes. And by evenly distributing requests, we prevent any single server from becoming a performance bottleneck. Crucially, intelligent load balancers continuously run health checks. If a backend cashier or server becomes unresponsive or overloaded, the load balancer dynamically removes it from the rotation, ensuring seamless user experience. Now, this is a very common aspect of distributed systems, which is that failure is inevitable, which means that what happens when a network request fails? We retry, but it has to be aggressive and immediate, which leads to things like cascading failures by overwhelming an already struggling service. We solve this by exponential backoff, progressively increasing the waiting time between retries, often adding random jitter to desynchronize client requests, which involves adding a simple delay of some milliseconds between consecutive requests. Retrying also introduces a new danger. What if the original request actually succeeded, but only the acknowledgement package was lost? This is why idempotency is non-negotiable. In mathematics and system design, an operation is idempotent if applying it multiple times produces the exact same result as applying it once. For example, when you're charging a credit card or updating a database, idempotency guarantees that retries never cause an unintended duplicate action. Then there are things of consistency models and consensus, which is used primarily in Bitcoin and such services. If we examine data accuracy through consistency models and consensus, industry applications operate on a spectrum. Financial systems often demand strong consistency, where every read is guaranteed a fresh read. Social media feeds, however, leverage eventual consistency, where replicas might temporarily diverge for higher performance, knowing they will eventually synchronize. An example of this is likes on YouTube. If you're watching a YouTube video and you send a like, the likes counter is getting data from all over the world, from everyone who might be seeing the video at the same time. Your like is instantly recorded as it shows the number is incremented, but if you reload, the number changes to a much higher value. That is why it is called eventual consistency. It is taking into consideration that sometime in the future the data might be accurate, but it doesn't have to be accurate right now. And now the thing is, how do distributed nodes agree on state when partial failures occur? There are consensus algorithms like Paxos and Raft. Think of leader election in Raft like coordinating a student group project. If the project leader suddenly disappears, the remaining team members initiate a structured voting protocol. A leader is elected by majority consensus, ensuring the project continues seamlessly without human intervention. And this now brings us to a new level. If it is a student group project, you can actually see physically who the leader is and what is happening. But in systems where there are hundreds and thousands of interconnected microservices, how do you debug an outage? You cannot SSH into 1,000 machines. You need observability. Effective observability rests on three pillars, which are logs, metrics, and traces. Logs give us granular, time-stamped records of discrete service events. Metrics provide aggregated statistical charts like CPU utilization, latency percentiles, and throughput. But the real superpower in distributed systems is distributed tracing. By injecting a unique correlation ID at the API gateway, tracing maps the entire lifecycle of a user request as it cascades through dozens of downstream microservices, allowing us to pinpoint exactly the latency bottleneck in seconds. Now let's map all these concepts to real-world architectures, starting with WhatsApp. WhatsApp is no less than an industry marvel. They handle over 2 billion users daily with fewer than 1,000 servers. How is that possible? They keep their backend intensively lightweight. As shown in the schematic, the client sends a message to a highly optimized routing tier and message queue. WhatsApp servers don't store your chat history permanently. Their primary job is asynchronous message brokering. Once the message queue confirms delivery to the recipient client, the server purges the payload from memory. This relentless focus on transient queuing and concurrency allows them to achieve astronomical server-to-user ratios. Now let's look at Netflix, which consumes a massive percentage of global internet bandwidth. Netflix separates its architecture into distinct layers. When you open the app, your requests hit their API gateways and backend microservices running in the cloud to authenticate, fetch recommendations, and manage user profiles. But when you hit play, you are no longer streaming from cloud data centers. Video content is delivered directly from OpenConnect, which is Netflix's proprietary content delivery network. That is installed inside local internet service provider networks. Netflix has collaborated with all major ISPs across the world to make sure that the data is delivered in a very fast manner. By pushing multi-gigabyte video files to physical network edge, Netflix eliminates cross-continental routing latency and saves millions in transit bandwidth costs. And next we come to Google Docs, which is the backbone of any student's life. How do 10 people edit the same sentence simultaneously without overwriting each other's work? This requires advanced state synchronization. Google Docs relies on operational transformation, or OT, and more recently CRDT concepts. Instead of sending the whole document states, clients transmit granular operation streams. Like for example, it goes something like insert character X at index 5 of any document. The central server then transforms these operations against concurrent keystrokes from other users to ensure convergence. Furthermore, to make the UI feel instantaneous despite network lags, docs use latency compensation. Your typing is applied locally and optimistically in real time, reconciling with the server asynchronously in the background. Now we come to UPI, which is what has enabled financial scale in all across India. UPI processed its first billion transactions in 2017 and reached to 2 billion monthly by 2020 and handles tens of billions of transactions today. UPI is a masterclass in interoperable, distributed routing. Whenever you scan a QR code, to initiate a secure distributed transaction across a four-party model. The payment request travels from your payment service provider, PSP app, which is apps like PhonePe or Google Pay or Beam UPI, and then it is brokered centrally through the NPCI switch. It is then routed to the payer's bank to debit funds, which also coordinates the payer's bank to credit the account and return an atomic confirmation. This manages strong consistency across disparate legacy banking systems at this scale, and it is one of the greatest engineering achievements in fintech history. Next, we come to Bitcoin. Final architectural example of Bitcoin. How do we achieve consensus when you cannot trust any of the participating nodes? This is one of the foundations of Bitcoin and blockchain in general. There has to be anonymity between the people participating in that certain software. Bitcoin solves this using Byzantine fault tolerance. It solves the Byzantine general problem using a decentralized ledger maintained by over 15,000 peer-to-peer nodes globally. Instead of a leader like Raft, Bitcoin uses proof of work. Miners expend computational energy to solve cryptographic puzzles, and the first one to solve it right gets to append it to the next block of transactions. Because each block contains the cryptographic hash of the previous block, the ledger is mathematically immutable. Altering a historical transaction would require recomputing the proof of work for that block and every subsequent block. And it would require to do it faster than the rest of the 15,000 nodes are uh, contributing to the network. From this, we see the common patterns in distributed networks. To summarize our journey, every large-scale application boils down to four core concerns: communication, coordination, handling failure, and balancing trade-offs. Whether you're building social media queues or banking switches, the patterns repeat. You will always rely on caching, partitioning, replication, and load balancing. For the academic researchers and system architects here, the frontier is wide open. Research heavily focuses on geo-distributed databases, achieving global consistency with lower latencies, CRDTs enabling offline-first collaborative software without central coordination, and pushing computation to the edge. I highly recommend diving into Martin Kleppmann's Designing Data-Intensive Applications and seminar papers like Google Spanner and Dynamo to deepen your knowledge. With that, I end my session. I thank everyone to listen so carefully and will be taking questions.
Thank you so much, Ojaswi, for such an informative session. Your real-world examples and clear explanations have given us a much better understanding of the engineering principles that power applications we use every day. We will now move on to the Q&A session. If you have any questions, please feel free to raise your hand and unmute yourself.
Ojaswi, I have one question. See, Netflix, WhatsApp, and Bitcoin, basically they serve a completely different purpose, like Netflix for video streaming and WhatsApp for real-time messaging and Bitcoin for decentralized finance. So what would be the single unifying challenge all three have to solve and how they are going ahead with it?
The single unifying challenge that they have is that they have a huge audience. They have to serve their requests, their services to a global scale. It is a population of 7 billion people that all of them have to be able to cater to. If it is WhatsApp, it has to make sure that all people can talk to each other, whether they are at one corner of the end or the other, if they are next to each other or if they are far apart. And same for Netflix. If you're very close to a Netflix server, or if you're very far away from a place where there are any servers, you should be able to see the movies and the streams that Netflix has.
Okay. In fact, maybe we could also put it in a different way, wherein WhatsApp prioritizes basically on availability and low latency, and Netflix will prioritize on availability, and Bitcoin will prioritize on security, consistency, etc. Right? I think what you said is right. I just want to add upon. I think And in fact, the question which I asked for on behalf of the, our target audience. And the other question is how students can go about where should students start to, get into distributed systems? How should they go about? What sort of international certifications or what sort of options are available for them to hone their skills in terms of distributed systems?
I feel the first step would be to check out the papers from Bitcoin's original creator, Satoshi Nakamoto. In 2007, he created the white papers and he launched them publicly on every platform. And they line out exactly how distributed systems work as we know it. From there, that would be a good standpoint. You can contribute to platforms of Web3 like Ethereum, where there's multiple fronts that research is being conducted on a daily basis.
Okay. Thank you, Ojaswi, for the informative and very useful session. Thank you.
Thank you so much, sir. Tamia has a question.
Yeah, I just wanted to ask, why does Google search return results in like milliseconds, even though it has to search billions of web pages?
Okay. So Google is one of the oldest pieces of search engines that there are. It doesn't search the entire internet every time you type a query. It continuously crawls and indexes web pages in advance, storing them in massive distributed databases. When you search, Google looks up the index data rather than scanning the web in real time, making the process extremely fast. To further reduce response time, Google also distributes its data across data centers worldwide. Yes, Siddhi.
Right. Am I audible?
Yes.
Okay. So we've noticed that, sometimes we've heard that, servers from like, let's say WhatsApp or Netflix, they do fail, right? That may be due to, excessive traffic or something like that. But even due to that, even due to a lot of servers failing at the same time, how do the applications, keep running? Because I understand the concept of load balancing here, but, still, if there's multiple servers failing at the same time, we still do have the applications running smoothly. So how does that work?
This is a combination of redundancy, replication, and automated recovery. So basically, redundancy means that all the data that the service has to provide, they are stored all across the world. There are multiple instances of their databases in different geographic regions. If one server or an entire data center fails, traffic is automatically redirected to healthy servers using load balancers, like you said, and failover mechanisms, ensuring users experience little to no downtime. Also, these platforms continuously monitor the health of their infrastructure using automated monitoring and observability tools. If a server becomes slow or unresponsive, it is quickly removed from the service while a replacement is started automatically.
Okay, that makes sense.
Tanishta,
Thank you.
Uh, During festivals, when there are sales like the Big Billion Sale or the Amazon Prime Day sales, we often see that these websites become very slow. So, how do these companies handle such traffic?
to handle all of these traffic, we again go for horizontal scaling because vertical scaling is not feasible for a country as big as India or a population as big as the world. We have multiple, we have softwares like Kubernetes using which you can have multiple platforms and multiple containers running your same code, running the same backend as microservices to better be available for all the people that are using it. This allows for people to have more availability during high traffic times. Aditya has a question.
Yes. So I have my same account logged in both of my Spotify accounts on my PC and my phone. And when I pause it on my phone, I can play it back from the same place where I left it on my computer. How does that happen? How does it remember where I left it or paused it?
Yes, so that seems to be a very Spotify centric question. But I would assume that every time you play or pause a song, Spotify must continuously update your playback state, including the current song, timestamp, and maybe even the next songs. Instead of storing this information only on your phone, it must be synchronized directly with Spotify's distributed cloud servers. When you open Spotify on another device using the same account, the device requests the latest playback state from the cloud instead of local storage. Then server then responds with the most recent information, allowing the song to resume from the exact point you left it at.
Thank you.
Yeah.
Thank you, everyone, for your enthusiastic participation. As we come to the end of today's webinar, I now invite Vaibhav Nangia, Chairperson, CSI Vellore Chapter, to propose the vote of thanks.
Good evening, all. I'm Weber, and I'll be addressing the vote of thanks for today evening. First of all, good evening, everyone. On behalf of the Computer Society of India Vellore chapter, I would like to extend my sincere gratitude to everyone who made today's session possible. A special thanks to Dr. Inya Nehru for gracing the session as our chief guest. I would also like to sincerely thank Mr. Sarvana Kumar R. and Mr. Subramanian for their constant support, guidance, and encouragement in making this session possible. Most importantly, I would also like to thank Ojaswi Om for delivering such an engaging and insightful session on the secret life of distributed systems. This session gave us an interesting perspective on how platforms like Netflix, WhatsApp, Bitcoin, and even Spotify tackle complex challenges to operate at such a massive global scale. I would also like to thank the CSI Region 7 chapters, the organizing team, and everyone who joined us this evening and actively participated in this session and the Q&A session. With that, we come to the end of today's webinar. Thank you once again for your time and participation, and have a wonderful evening.
Yeah, before we wind up, I just want to request all of you to stay tuned for our monthly webinars, which is going to continue every month. Last Saturday of every month, we